Alright, so we continue to practice our skills, our excellent calculus skills on parametric equations. This is all the same that you've done in a previous semester calculus course, but today we're doing it with t's and parametric equations. Alright, so let's do a little arc length, yeah? Arc length, roughly speaking, means you got to figure out how long these lines are, the length of them. So in this case, we've got some standard parametric equation. We got our boundaries here, t equals to 1. That would mean x is equal to 1. When t is equal to 2, x is equal to 4. So we're doing this piece right here. We're trying to figure out how long is this piece. We cut it up into infinite many little diagonals, each of length ds. We make a little baby tiny microscopic Pythagorean theorem, a right triangle here. And we get the excellent relationship that says that ds square is equal to dx square plus dy square. That would imply that ds is equal to the square root of dx, the quantity squared, plus dy, the quantity squared. And of course we're trying to add them all up using the amazing grace and elegance of the fundamental theorem of calculus. And here we go now. We've got some choices to make. This is in terms of dx. I've got dx's and dy's. I kind of like only, if I have one integral, I only like one variable here, not a bunch of them. So you got to get rid of the dx or get rid of the dy, or maybe get rid of both of them in exchange for dt's. Since today's I'm feeling kind of parametric, why don't we go with t's? Can we exchange everything for t's? And the answer is yes, we can. It'll go something like this. So here I slap a d on both sides and I get that dx is equal to 2t dt. That's going to be my exchange rate for the dx. Here I get that dy is equal to 3t squared dt. That's my exchange rate for dy. That forces this one to be the square root of dx squared. So I got to square both of these sides. That would give me 4t squared dt squared. And I got to do dy squared. That would give me 9t to the 4th times dt squared. Okay. And I could clean this up a little bit. That would give me 4t squared plus 9t to the 4th. And I could factor out a dt squared out of both of these. It would come out like that. Maybe I could do better than that. I could factor out a t squared. So that would give me a t times the square root of 4 plus 9t squared dt. So the t squared here and a t squared there came out as a single t, leaving only a 4 plus a 9t squared. I can maybe try for a u sub here. I don't know, I'm not afraid. U is equal to 4 plus 9t squared. That would force du to be equal to 18t dt. I have a t and a dt there. That can be exchanged for a 1 over 18 du. That's the exchange rate for t dt. Holy cow, I'm getting t'd out. So this becomes, let's go back to green. Green. Nice. Alright, so that would be 1 over 18 integral of u to the 1/2, that's this piece, t dt, that would give you du. Alright, so this becomes 1 over 18 times u, I gotta add 1 to it, divided by the new one, and my grand total would be, of course, 1 over 18 times 2 over 3 times u, which was 4 plus 9t squared to the 3/2, and my t's going from 1 to 2. So you plug in the 2 and you plug in the 1, and the rest of that is so boring. Forget about it. I'm not doing that. Alright, too easy. You guys can finish that. Still, I think this problem was kind of easy. Should we try something a little bit more challenging? Maybe, maybe not. How about this? What if I propose the following? This right here caused a lot of trouble for people. Finding the arc length of an ellipse. How long is it? You saw earlier we found the area of the ellipse. Now how about, can we find out the length of it? You know, for a circle it's quite easy. For a circle, if this r, the circumference is equal to 2 pi r, right? What would it be for an ellipse? A shape where this is A and this is B, or whatever. What would the circumference be? That's what this problem boils down to. And I invite you to try it on your own, just for fun, with some espresso and some good music and fireplace on a rainy day. You'll have lots of fun with this one. I think we should stop here. That's a good little introduction to parametric equations. Very, very good from beginning to end, what they are, how do you graph them, did some calculus on them, and of course we looked at one of the most famous parametric equations of all times, the cycloid. You should look that up, by the way. A lot of interesting reading to do on that. Entire books have been written on the cycloid. Alright, I think my time here is up for today. We should make that call it a night. We'll see you guys.
I got a ticket for